Hello, my name is Chloe Kim from Cornerstone Collegiate Academy of Seoul. Today, I'll present our work on attention-enhanced speaker invariant deepfake detection. Our model is designed to defend against AI-driven voice phishing that imitates speaker-specific to deceive family members, colleagues, and acquaintances. As synthetic voice generation became more advanced, the risk associated with audio manipulation grew rapidly. Our goal is to develop a detection framework that is independent of speaker identity and capable of generalizing generation-related patterns. I want to start my presentation with problem overview. AI voice phishing has emerged as one of the fastest growing cybersecurity threats. Attackers no longer use generic synthetic voices. Instead, they impersonate real individuals, family members, employers, and government officials to conduct social engineering attacks. Modern deepfakes replicate not only vocal tones, but also rhythm, emotions, and prosody. However, most existing detection systems rely heavily on speaker-specific information. As a result, they perform well on familiar speakers, but fail when encountering unseen voices or new recording conditions. This lack of generalization poses a serious challenge for real-world defense. Then, how is the traditional method, and how are they limited? Traditional models focus on cues like speaker identity, style consistency, or simple waveform distortions. These cues used to be effective when deepfake contained noticeable artifacts. However, modern text-to-speech and voice conversion technologies have eliminated many of these weaknesses. Today's synthetic voice can closely replicate emotional fluctuations, natural rhythm, and articulation. Therefore, older detection cues are no longer sufficient to expose modern deepfakes, creating an urgent need for deeper and more robust approaches. So, our research shifts the perspective from asking who is speaking to how was the voice generated. In practice, this means detecting generation specific patterns that appear during artificial synthesis rather than identifying speaker related characteristics. By focusing on how the voice is generated, our model can generalize effectively to speakers it has never seen before, an essential requirement for real-world deployment. Our full pipeline works as follows. Audio is converted into MEL spectrogram to capture time frequency information. And the spectrogram passes through the retina backbone with CBAM modules for enhanced feature extraction. Features are processed by the speaker devising module to remove identity cues. A classifier then determines whether the speech is real or synthetic. The system is trained end-to-end to align attention learning, identity removal, and detection performance. Then, let's talk about proposed framework. Our framework consists of two core mechanisms. First, we integrate on attention-enhanced featured learning modules using CBAM, Convolutional Block Attention Module. This highlights acoustic regions where synthetic voices often exhibit irregularities, such as unnatural spectral transitions, subtle high-frequency artifacts, and timing inconsistencies. Second, we introduce a speaker invariant representation module by moving identity information from feature embeddings. The model focuses solely on generation-related artifacts. Together, these components enable robust generalization and improved detection of deepfake exhibiting irregular prosody. Then, how does the CBAM contribute to our model? CBAM strengthens the model's ability to capture both local and also global cues. Regular CNNs effectively detect local details but often miss broader patterns like rhythm and prosody. CBAM addresses this by identifying the most informative frequency channels, highlighting key time frequency regions where anomalies occur, enhancing subtle transitions that standard CNNs may overlook. This enables the model to detect fine-grained irregularities characteristics of synthetic speech. Then I want to talk about how CBAM is integrated in our model. In our architecture, CBAM is embedded into intermediate layers of ResNet 18 backbone. Placing CBAM at multiple depths allows the network to refine attention across both shallow and deep feature maps. This design improves the model's ability to capture meaningful local and global cues, allowing reliable detection even when defects exhibit high fidelity. Then, I want to talk about speaker devising module. The speaker devising module ensures the model does not rely on speaker identity, which is our key goal in our research. Real-world attacks often target individuals the system has never encountered, making reliance on speaker-specific cues ineffective. Through adversarial training and a gradient reversal mechanism, identity information is actively removed from the feature space. A bottleneck layer further compresses representations to suppress identity leakage. This process ensures the model learns only generated generation-related artifacts, improving performance on unfamiliar voices. Then, I want to talk about our experimental setups. We evaluated our model using two main datasets. ASB Spoof 2019, a widely used benchmark for deepfake detection. A custom voice phishing dataset that includes impersonation, attacks, and varied recording environments. The model was implemented in PyTorch and trained on NVIDIA RTX 300 GPU. We compared performance against CNNs, transformer-based models, and specialized detectors such as AppSet and VoiceReader to ensure fair and comprehensive evaluations. This is our quantitative data result. Then I want to highlight our noticeable performance. Our model achieved slightly above 90% accuracy and operate at 28 frames per second, enabling real-time deployment. Compared with CNN detectors, accuracy improved by 3 to 5%. Compared with larger transformer models, our approach offers similar accuracy at much lower computational cost. Although some heavy models achieve higher accuracy, they are too slow for real-time defense applications. Our method strikes a strong balance between accuracy, speed, and generalization, making it highly suitable for preventing voice phishing attempts. Instant normalization and time masking significantly improve representation quality. With this preprocessing enhancement, accuracy increased from 90.8% to 93.3%. Training also became more stable with fewer oscillations during optimization. This result shows that preprocessing and attention-based feature learning complement each other in building a stronger detector. And this is our other quantitative data result. We compared our Brier score and our ECE percentage with other different models, such as ResNet, DenseNet, EfficientNet, and other models. For example, ResNet got 6.8% ECE, but our got 3.2% ECE. Our models got the lowest ECE. Then, this result connects with the reliability. Beyond accuracy, we evaluated prediction reliability using calibration metrics. Our model achieved the lowest calibration error among all compared systems, meaning its confidence scores are most trustworthy. In real-world fraud detections, poorly calibrated models can give dangerous false assurances. Our approach avoids these issues by maintaining stable and well calibrated predictions. Then, I want to talk about our key takeaways from my experiment. CBAM attention and speaker debiasing focus on generation related patterns, and the system detects impersonation based deepfake robustly. It achieves real time inference at 28 FPS. It improves accuracy and prediction calibration. It remains robust across different speakers and environments. The things that I want to improve for the future work include expanding dataset to cover more languages and cultural speech patterns. We also plan to integrate visual cues, such as lip movement, to build multimodal detection systems. Lightweight versions for mobile and embedded devices can be developed using modal distillation or pruning. Finally, API-based deployment could offer practical defense solutions for communication platforms. In summary, combining attention mechanism with speaker invariant learning provides a strong and scalable defense against modal voice deepfakes. Our framework improves accuracy, robustness, and real-time usability. As synthetic voice continues to advance, approaches like ours will be essential for maintaining trust and protecting users from impersonation based attacks. Thank you for listening to my speech.